Okay, we start up again. So now I want to give you an alternative, which I think is better for handling, say, output from OpenFOAM. As an example, I'm going to use the elbow tutorial, if we can find it. If I can find my glasses. Let's try that one. Let's see now. I'm in my run folder. Let's see, find inside the tutorial folder from tutorials, and it should be a directory and the name should be elbow. Yeah, I found it. It's under incompressible icofoam, so hence it's a laminar problem. Never mind. Copy -R and then the entire tutorial setup like that. Oh, not like that. Like Control-C, like that, and copy it to my run folder. Now I have the elbow case. Here we are. Here we have an elbow case, but quite frequently when you find a tutorial, then the setup may look a little bit strange. Well, we have a system and a constant folder, and that makes sense, but I have no zero folder. I have something called zero original, whatever that might be. So the setup here is a little off, but very, very often you will then have this all run file. Inside that one, you will sort of have the recipe how to do this, say, tutorial. So you can just write all run and then he will execute it. That would be the cheap way to do it. You can have a look inside this all run file to see what he actually does. And then he does some cryptic things, starting a shell here, and then restore 0dir, whatever that might be. And then he's using something, something, and then he's using something, and then he's using something. You have the recipe here, what he's actually going to do. This one here is quite Greek, so I don't care about that one. But I'm going to need this file. I'm going to need this file. So let's copy that one. Copy this file. Should be under tutorials. Let's try it like that. Then of course this is a shell script inside this all run, so I don't need this strange syntax, so I just use form tutorials like that. Let's see if this one works. So here we go. Yeah, it works. Now I have this elbow MSH file. And here comes the point. That file, MSH, that is taken from Fluent, from Ansys Fluent. This is a mesh created at another software. It's not a structured mesh. We'll have a look at it later. So how can OpenFOAM then use mesh from other software? So the next sort of tasks in this course will be then to deal with more complex geometries. Block mesh systems can only do so and so much, but more of that later. But for now, okay, we have gotten a mesh from somebody. Let's use that one. Then we do it crudely here. Fluent mesh to foam. If you look at the user guide, you have plenty of these programs. Fluent mesh, you have a whole bunch of these programs that can sort of translate the meshes into something that OpenFOAM hopefully can understand. So this was the name of the program, and then we need the name of the mesh file. Let's see if this one runs. What do you know? Looks okay. Looks okay. What he has done, maybe not so easy to see here, but oh, he has done a lot of things. Doesn't seem to crash. Let's try a check mesh just for fun here. Check mesh. Yeah, mesh is okay. Okay. What kind of mesh are we talking about here? Well, we don't have any hexahedras as we normally have when you have rectangular cell systems. We have prisms. Oh, that sounds interesting. We don't have that many, so it's not a big mesh. But never mind. It seems to be working. If you want to have a look at, say, this Fluent mesh file, this is not for amateurs. This is then created from ANSYS Fluent, and if you look at it, the logic here can be, to say the least, pretty messy. And here you have ordinary numbers. And then down here, all of a sudden, now it switches. Here is hexa numbers. Okay, be my guest. So the logic behind such a file is not so interesting. What might be interesting is all the way at the end. And this is also quite essential, actually. Say you are creating a mesh in ANSYS, later to be used in OpenFOAM. You need names in OpenFOAM. You need an inlet, you need an outlet, you need walls, internal fields. You need these different names because later you then have to fight with your zero folder for the boundary conditions. So you have to know what are the names of the different walls. Do I have an inlet? Do I have an outlet? So maybe these names, they might be quite crucial to find. So it's not just called inlet, it's called velocity inlet -5. And okay, it's just a name. But you need to know these names. So at the end of such a Fluent file, actually you can find them. Still, the check mesh, he will also give you the different patches that he has identified. So we have wall 4, velocity inlet 5, inlet 6. We have 2 inlets, okay. And we have 1 outlet, and we have a wall, and we also have front and back. Nice. So it's a 2D thing. Okay, so good. So this is now should be ready to run, but to be able to run it, now we have the mesh, and the mesh is okay. I need my zero folder, but I only have this mesh, strangely, zero original. What's that? Let's have a look. Zero original. There I have a U and a P file, as I should in an ordinary zero folder. And I guess they look okay. We can open one of them. Run elbow 0 original. Yeah, let's have a look at the velocity here. Yeah, he looks like he should be wall number 4, type no slip, velocity inlet 5, 1 meters per second, inlet 6, 3 meters per second in the y direction. Okay, and then we have a pressure outlet. Okay. So yeah, this seems to be the normal type of zero files, but I can't really use this zero.original. OpenFOAM requires just a 0 here. So what do? Copy -R, 0 original to 0. So there I have just copied the entire folder and then into just a pure 0 folder. You could have used move, then you have just renamed him. That's another way to do it. But now we should be good to go. You might think. Let's have a look at the mesh first before we do anything. No, that was wrong. Here we are, and apply. So this is an elbow. Not my elbow, but an elbow. Let's have a look at the mesh here. There you have it. So yeah, you have an inlet here, sending in 1 meters per second. Then you have a tiny little inlet here, sending in 3 meters per second. So you get a jet inside the elbow, and then you have the outlet. But you see the mesh system, totally unstructured. Totally unstructured. Okay, that was a mesh. I don't think we are allowed to do, no, we are not. Never mind. Then this is something you should be aware of. For this problem here, it's not so important. We only had under 1,000 cells, so no big deal. But if it's a big problem given by somebody else, or if you have messed it up yourself with a little bit strange block mesh dict file, you should actually do the following. If you write renumber mesh, nothing more, renumber mesh, you get the following information here. We have 918 cells. And here, before renumbering, he says band is 735. And then after renumbering, band is 29. What does he mean by that? What does he mean by that? So this was the sort of the geometry. How has Fluid organized this mesh system? We don't know. Maybe here is cell number 1, cell number 2, 3, 4, 5, 6, 7. It can be totally random, the sequence, how this is organized. Okay? And then what do you have to do after you have a mesh? Well, you discreticize your equation system and you end up with something like this. A multiplied with your unknown x equals a right-hand side. This one is a matrix, a coefficient matrix. Looks something like this. Multiplied with a vector of all your unknowns, x1, x2, all the way down, equals a right-hand side. It's a linear equation system. And yes, we don't have that many unknown in this problem with, say, 1,000 cells. So you have 1,000 u velocities, 1,000 pressure, 1,000 v velocities. Not that many. To be able to solve such an equation system, we need solvers. And we try to use the fast one, of course. But these fast solvers that we are using, multigrid, Krylov methods, they will have to address this coefficient matrix to try to make this one run fast. And as such, a coefficient matrix, typically, he will consist with several diagonals here, or also off diagonals. Of course, the diagonal, that will just be the unknown themselves. But you will typically here maybe use some of the neighbor. If you are calculating x2, then maybe you need x1 and x3 as neighbor values, depending on your numerical scheme. And how this is organized, that will sort of decide how this A matrix will look like. It's going to be mostly zeros. But when you have something different from 0, it will then be part of any of these diagonals. And this is what we call bands. And the number of bands here, the smaller the better. The narrower this number of bands is, much faster the solution will be. So this is quite essential for big problems. And as the renumber command said, renumber mesh, he said 783 before renumbering, meaning they have created this mesh totally messy, quite randomly organized. That's not smart. If we had renumber it more, say, smoothly, then we reduce the number of bands here all the way down to, what was it, 29. So, and that's a huge gain. And for a big problem, you have 1 million unknowns. This then will be 1 million by 1 million matrix. Of course, you don't store it, but it's essential then the number of band here has to be as small as possible. So yes, you renumber your mesh. Very important. For this cute little problem here, no big deal, but no questions to that one? Then let's go back. So when you just write renumber mesh, he just gives you this information. And then you can see here, I get a huge gain if I do this. But to sort of make it permanent, you have to write renumber mesh space minus overwrite. Then he will organize the mesh and then destroy the old one and get a better new one. So minus overwrite. Over, maybe not the big W there. Overwrite. There we go. So now I have a new and better mesh. Yes?
Should you use this command for every case or only large cases?
Should you use it for every case? Well, you don't do anything wrong by doing it. But, I mean, if you have a case, you start a simulation, and it takes hours on end, and then you have to do something. Then this might help a lot. But if your simulation takes 10 minutes, who cares? Your choice. So you can do this anytime. Normally, when you create a mesh with block mesh, then he's pretty well organized already. But you can try it. You can try it. Other questions? Okay. Now let's have a look at the solution. Well, we don't have the solution yet, have we? No. You have to simulate first. Icofoam. Let's see now. There he runs and there he's done. So, yeah. Don't take too long time. A Courant number of 0.5 looks nice. Shouldn't be a problem. Let's have a look. Parafoam. So we can start with a velocity, and then we run. Here we go. So we have an inlet here, quite thick boundary layers, little strange bump here, whatever that might be. Then we have an inlet here, sort of a jet hitting inside this elbow, and then the outlet. Looks reasonable. And if you want to have a look at the mesh as well, surface with edges. Say now, from this result, I want the correct data given from OpenFOAM. They are going to be located in the center of each of these triangles, a little bit randomly distributed. But here I want things like maybe a velocity profile, I want the pressure gradient, I want whatever. How the heck are you going to handle that one? Ooh, nasty. But you have already been given a solution. Should be here somewhere. I think I put it out under material, OpenFOAM. Read original OpenFOAM data in Matlab. So here you have a cute little M file, and then we have some two results files, and then we have this C file. I discussed this earlier. You can obtain the position, the location for each cell centers by one of these commands. Now I cheat. I have loaded the program in here already. So after one simulation, if you execute this write cell centers, then you'll get these C files. And here, I think I have the different C files here. Let's open that one so we can have a look at it. So this is the C file from this elbow case. I already copied it. We had 918 cells, or triangles, makes sense. So here you find the X, Y, and Z position at the center of each of these triangles. So of course you could use cut and paste from this file. Let's see now, 900 should be down here somewhere. Here we are. But then also you have sort of separate numbers depending on the different boundary patches that you have been using. We had a solid wall and we have a 100 sort of faces there. And here you have the location for these wall points. And then you have the location for the different, say, the inlet. Not that many, so fairly easy to see. And also the inlet number 6, you have them listed here horizontally. And also the outlet. And then actually we have a wall number 8 as well. We have one top wall and a bottom wall. So the top wall is only 34 points. So yeah, you can use this C file with cut and paste. What else do you then need? Well, they have to match your result files. So this one is taken directly from, say, the latest time, the U result file. And you see 918, but sort of where are these velocities located? It doesn't say. Hence, you need this C file to match these two. Okay, so just to show you now, I have written here a Matlab script that then actually can read these different files and then scan them and sort of filter out the needed information. So I do that for the U file and the P file, and I also do it for the C file, the position file. So let's now see here at the end here. So at this point, I now have the X and Y positions, and also have X and Y positions for the different boundary points. So I can plot them. I have the velocity field given at this location for the mesh. So yeah, we can make an easy figure here first. Let's try that one. If I run this one. He should then give me something like this. So here you can see it's okay. He has actually found the correct information. Blue dots, blue circles, they are the center points for each triangle. The red circles, they are the boundary points. And I even put in here a vector plot with quiver in Matlab. That's actually possible. So yes, you have all the information. So yeah, you can plot a figure out of this if you like. But typically now, if you want to do things like a velocity profile, then we have to interpolate a lot here. Now, you have something nice in Matlab. It's called scattered interpolant. Scattered interpolant. Meaning you have some original data randomly distributed in space. And you use that one as an input into, say, a system here. that you later then can interpolate this velocity. Here I shuffled in locations randomly distributed and then the corresponding x velocity. So then afterwards you can find the x velocity wherever you want by simply saying this function fu with now different locations, and then you have the corresponding velocity at that location. So this scattered interpolant is actually a quite nice function in Matlab. So here I now have created say one line in the y direction here, and I have a position in x. I just use a quiver to create some velocity vectors there. Here I create another line at another location. We can look at that one later. And then finally, figure number 3. Here I'm now pushing the pressure into this scattered interpolant and have a function that can now give me pressure anywhere I want. And then I create just a line inside my domain and say I want to have the pressure along this line. Okay, then I have to use this information from this function at the different locations along that line. So if we run this one, you will see it. Let's see now, figure number 2. So here then, I just have a small gray dot to show you the different cell centers. So here I have a velocity profile, very nicely indeed. And here I had another one. Now you have to be careful using this Matlab function, scattered interpolant, because here I could actually specify a velocity profile along a line all the way up here, outside the computational domain. He will still give you an answer. So we sort of interpolate from inside the entire rectangular domain here. So it can be pretty stupid, so you have to know what you're doing. But if you are inside the domain, like this, yeah, that should be quite nice. And then finally, the pressure. So here I have just chosen some arbitrary points along a line throughout the elbow, and then I want here, what is the pressure along this red dotted line? Again, this scattered interpolant is actually quite strong, and he gives me then quite easily what I want. So I think this is a good way to sort of extract the data from OpenFOAM and put them exactly where you want them. And also he's based on the original center data, not from Parafoam where he has interpolated something. So I think I will recommend this one. As you have been given here then this Matlab file, and then this example from this elbow case. So yeah, I can recommend that one, I think. As I said, continuation in this course now will start looking into more complex mesh systems. So that will sort of be the topic for the theory next week, using something called snappy hex mesh that can resolve quite complex geometries within block mesh. And then maybe we have to look at some external software that can create meshes for us. We'll have a look.